So this week, we will cover the fundamental theorem of calculus, or today we'll cover the fundamental theorem of calculus. Yesterday, we started to discuss integrals, definite and indefinite integrals. Definite integrals give an area between a function and the x-axis, where it treats the areas above the x-axis as positive and below the x-axis as negative. Indefinite integrals give families of antiderivatives. And the fundamental theorem of calculus, one of the things it does is shows that those two integrals actually are very nicely related. But before we get into that, let's cover 5 properties of the definite integral. So for these, well, let's look at part A. For part A, we notice we do have a definite integral because we have bounds on our integral. The lower bound is lowercase a, the upper bound is lowercase a as well. So part A, we have the integral from a to a of a function. And what's that going to equal? Well, I guess I'll draw it here and then erase it when I get to part B. So we have a function. Here's a. What is the integral from a to a measuring? Well, the integral from a to b measures some area between a curve on an entire integral. But a to a is looking at what happens just above a. And the rectangles you could form to approximate the area and then take the limit are going to have no width in each case, meaning they will have area 0. And as you let the number of rectangles go to infinity, you will have 0 area in each case. So that integral is 0. Any questions about the first property? Now, the second property, normally we consider integrals from a to b, but here we have an integral from b to a. And what this does, integral from a to b, well, maybe I'll write it like this so it's consistent with that notation. Integral from b to a would give us this area. But if we flip these around and instead make this our starting point, the rectangles we form, the base of each rectangle would actually be a negative, because it would be, if you have a base over here, and say the right end point was 4, the left end point was 5, then the length of that piece, if we're starting from this side, would be 4 minus 5, which is negative. The function is still going to be the same, but because the bases of the rectangles are going to be negatives of what they would be if you did them in the other direction, the integral from b to a equals the negative of the integral from a to b. So if you have an integral and for some reason you want to flip the bounds around, you can do that, but it makes it a negative. Any questions about those first 2 properties? We'll use most of these properties in some of our computations. Now there's one on the worksheet that uses part B. I think it's number 2, maybe number 3, part C, integral from 5 to 4 for the one that you have the graph. Part C, for indefinite integrals, meaning integrals without these bounds, we had that the integral of sums and difference could be done piece by piece. That works for definite integrals as well. If you have 2 functions added together and you approximate the rectangles, well, you can break it into the 2 pieces. I won't go into this one in much detail, like I did the first 2. But the same property applies. As applied in limits and derivatives and indefinite integrals, it now also applies to definite integrals. If you have a few things added together, you can do them piece by piece. And also, if you have a constant times a function, you can pull that constant out of the integral. These properties C and D work for all of the calculus constructs we've considered. Now, just like with antiderivatives, with well, really just antiderivatives, there isn't going to be a product rule for functions, but there is for the constant. So if we have a constant in front, we're doing a definite integral, you can pull that constant out. Any questions about C or D? Okay, now part E, what does part E say? Well, maybe I'll finish the sentence. I guess those would be equal. What does part E say? Part E, in many ways, is the nicest of these five visually. So let's draw a visual for part E. So what do we have? We'll assume for visual purposes that our function's above the x-axis. Similar arguments work if it goes through the x-axis. We have an integral on the left side. We have an integral from A to B. So we're looking at this area in here. Do I have colors? Yes, I do. We're looking at that area in there. Well, this part E says we can break that into two pieces. We can split this integral into two pieces. We can split that area into two pieces. If we put a C value between A and B, well, the area from A to B is now the area from A to C plus the area from C to B. And that works, if you extend that to integrals as well. And that C value can be anywhere between A and B. It's usually written without the equal signs because, with the equal signs, meaning over here, this is usually written without the equal signs. But it does hold for equals, because of property 1, if they're equal, 1 with 0. But the more interesting case is when C is between those two, because we can split an area into two pieces, but we can reinterpret that splitting of the area into splitting the integral. And we'll see that that is useful for something that we do in a few minutes. Any questions about these properties? Okay, let's first write the fundamental theorem of calculus. Now, as I mentioned before, fundamental theorem of calculus has two parts, and both parts have computations we'll cover. I guess I'll write this across the two boards. So all we need here is a continuous function. So it may not be differentiable everywhere, but it is continuous. If it's not continuous, then you can break it into its pieces. But let's let f of x be continuous on A to B. Part 1. If we're going to define a new function, capital F. How is this going to be organized? I guess I'm going to write part 1 over there. I wrote these first two parts pretty big. Part 1. Capital F. Remember, we have this notation I introduced yesterday, what I mentioned yesterday. Colon equals means we're defining. So we're defining capital F to be this function. More on that in a moment, but notice capital F is a function of x. X is up there. So it is a function of x. A is a constant. But capital F is defined to give certain areas based on which x value is considered. Then, what? If capital F is defined to be that integral, then capital F prime equals lowercase f on all of a to b, and f of x is continuous. Now, what does this all mean? Well, it actually means a couple things. I'll give you a moment to write it down. Part 2, I'm going to have to write over here. So I'll start erasing. Now, what are some of the consequences of this first part of fundamental theorem of calculus? Well, one, we have derivatives, we have antiderivatives, but we saw, for example, that product rule doesn't apply to doing antiderivatives, meaning if you wanted to find antiderivative of, say, x squared e to the x squared, something like that. If you wanted to find an antiderivative of that, well, there's no product rule. None of the rules we have apply to this. So it's not immediately obvious that that function actually does have an antiderivative. There are a lot of others, like even tangent of x. Unless you carefully look back at one of the problems we did earlier, we don't necessarily know that tangent has a derivative or an antiderivative, similar for cosecant and secant. But what this function says, given lowercase f, then capital F prime does equal f of x, meaning this capital F is its antiderivative. So one consequence of this is that given a continuous function, an antiderivative definitely does exist. It fills in kind of a large hole in our antiderivative computation. This line here says all continuous functions have an antiderivative, even if none of our rules apply to that function. Any questions about that first part? Second part, this capital F is continuous. Do I want to discuss that now or not now? I already wrote 2. Well, I'll discuss this now, and I'm going to erase my 2 up here because the visual we're going to get from this being continuous is pretty useful. So we have as our definition of continuous, the limit from the left equals the limit on the right equals the function. We also have the observation that you could draw the curve without lifting your writing implement. But what does this capital F of x look like? What does the curve capital F of x look like? Well, that's certainly not clear. What is clear? What is clear is that capital F gives us an area. What area does it give? Well, let's draw that area. Starting at A, function is continuous on A to B. I'll just draw it continuous everywhere. B is, let's say, here. What does capital F, oh, this is lowercase f. This curve is lowercase f. What does capital F look like? Well, it looks like, well, it gives the area between f of x and the x-axis between a and x. Let's take an x, that's after a. Capital F of x gives that area. And notice x is our variable here. So this x value we can move from left to right. This function is continuous, the function that gives these areas. How can we interpret that? Well, any questions about what capital F, yeah, maybe I'll write that down. Capital F of x gives that area. And x is a variable. So that x can move all over the place and capital F will still give that area. Any questions about that observation? Now, what does it mean for this to be continuous? Well, the definition of continuous is not what we say it is in Calc 1. The definition of continuous that we give in Calc 1 is useful visually. Now, this last conclusion, capital F is continuous, is very difficult to interpret, maybe even impossible to interpret with the continuous definition. You could draw it without a writing point. But what can we conclude? Or what can we say? Well, what I like to say, and what I like to see in a curve like this, is that this, that erased it somehow. This vertical bar, now at x, we can view this area between A and B as being filled in by these vertical bars. And we can let these vertical bars extend in either direction, and it'll fill in this area in a continuous way. A visual I always get with this is, if you ever use a scanner, and you see that blue or white stripe going from front to back, I always see that happening for these. And I always see a scanner going across this and just filling in this area until it stops. I find that visual very useful. In Calc 1, it may not be as useful as, well, it won't be as relevant in Calc 1. Making it useful won't be as relevant in Calc 1 as it would be in a future calculus class. Pretty much a couple things in Calc 2, but more in Calc 3. But a lot of Calc 2 and Calc 3 involves setting up integrals. And I find having that visual in the back of my mind is very useful for setting up integrals. Because to set them up, you would need an endpoint, you would need an endpoint, and you would need the top and the bottom of that stripe. So for those of you who are taking Calc 2 or Calc 3, I find it useful to have that somewhere in my mind when you have to set up integrals. A couple things at the beginning of Calc 2 when you do areas and volumes. A lot of things in Calc 3. And that's all a consequence of this capital F being continuous. You can fill in that area in kind of a continuous way by letting that x go anywhere from A to B. So any questions about the consequences we just discussed of the first part? Okay, we'll do a couple computations using this. But first, let's discuss the second part, and then we'll do some computations in the first part, then we'll have to do computations using the second part. To this point, if we want to compute a definite integral for a given function, then we would have to set up an approximation using rectangles. We would have to take a limit. We would have to hope that limit conveniently evaluates. But the second part of the fundamental theorem of calculus says we don't actually have to go through all of that. Second part relates our definite integrals to our indefinite integrals. Second part says that the integral from a to b of the function in question is given by capital F of b minus capital F of a. Notice b and a are the endpoint. B and a are the endpoints. So here on the left side, I have to tell you what capital F is. On the left side, we have a definite integral. On the right side, we have a new function evaluated at the endpoints, and we're subtracting. What is that new function? Well, the second part says that that new function, so where capital F is any antiderivative of lowercase f. This can be any antiderivative, or on the any part when we do some computations. But this part relates very nicely our definite integrals to our indefinite integrals, because remember, our indefinite integral gives us all antiderivatives. So here we need one antiderivative. So this part relates very nicely our definite integrals and our indefinite integrals. Any questions about the statements of the fundamental theorem of calculus? Okay. So let's do some computations. We'll do 4 or 5 computations using the first part, and then we'll do probably more than 5 using the second part. There's one other consequence of the first part. I probably should have mentioned this while it was written. So the first part says if capital F is the definite integral of lowercase f, then capital F prime equals lowercase f. Yeah, I definitely should have mentioned this while it was written. I actually should have mentioned 2 things while it was written. So the first part, the computations we will do using the first part use this part of the statement, the first part of fundamental theorem of calculus. If capital F is a definite integral, then capital F prime is lowercase f. What we're actually doing here is taking the derivative of this top line. The derivative of this top line is the derivative of a definite integral. And notice, if you take the derivative of the left side with respect to x, you get f prime of x. If you take the derivative of the right side with respect to x, well, you're just left with something involving lowercase f, meaning it kind of looks like the derivative and the integral are canceling each other out. And in a way, it does. Well, in a way, they do. We will see that in a way in our computations. One other thing about the first part, there's that variable t. Why does that show up? Well, I guess I'll mention that during these examples. In these examples, what we're going to do is find capital F prime of x. So we're going to take derivatives of integrals. Part A. There are going to be Let's do 4 of these. Capital F equals integral from, and let's do 1 up to root x of sine of t dt, and then we'll do 2 more after this. So there will be parts A, B, C, and D, but I'll write C and D after we do the computations for A and B. So here we want capital F prime, we want the derivative of a definite integral. Well, the first part of the fundamental theorem tells us how we can do that if we're careful with our derivative rules. What does that mean? Well, let's do part A. Well, before doing part A, let's recall the brief statement of the fundamental theorem of calculus. That's then. First part says, and you don't have to rewrite this, you wrote it in your notes already. First part says we have an integral from a constant to x. Oh, yeah. One other thing that I just mentioned that the first part says is we can take a derivative of this function. We have another derivative rule here. If that is our setup, then we can find its derivative. Now, what is the setup? Well, we have a number. Well, first we have a continuous function on our interval. We have a number, a at the bottom. We have variable x at the top. So right here, we have a derivative rule for a function of just x. When that happens, we can take the derivative by considering the integrand as a function of x. Fundamental theorem of calculus is a lot of words, so we'll abbreviate it FTC, part 1. So part A, by this statement up here of the fundamental theorem of calculus, capital F prime is 1 over x cubed plus 1. Any questions about that? We are reconsidering the integrand as a function of x. And that's what we did here. Any questions about part 1 or part A? Now, what is that variable t? Why is there a t that seems to randomly appear? You know, we've been usually trying to be consistent in using x's. Well, the x variable that capital F is a function of is already taken up. So to fill in the integral, we need a new variable since x is taken and t is standard for that application. So any questions about part A? Okay, I'm going to erase part A over here and do part B, because part B will take up more room. Part A, we had a function with just an x. The derivative rule that the first part of fundamental theorem of calculus gives us tells us what happens when there's just an x. Where have we heard that before? Well, what do we have here? Part B. We still have a number at the bottom, so that is consistent with the statement of the first part. But now we have a root x on top. We also changed the integrand here to sine. But the first part does not apply directly to this statement or to this equation in part B. because while there is a number at the bottom, there's now a root x on top rather than an x. For first part, we need a single variable with nothing else on the top. But what we can do here is make a substitution that will cause this function to look like a function on which that statement applies. Let's use u. Those are substitutions we've made. So here, if we let u equal root x, then f is now a function of u. Maybe I should make this u. And that really is. Well, I guess I'll say over here that f is now a function of u. And those equal signs are technically correct with the substitution. But now we can take the derivative of this piece using the first part. We can take the derivative of this piece as we've done before. And because we've made a substitution and removed all x's, we can apply the chain rule. So I'll say then f prime of x, which is what we want, equals, now we have the prime notation, we have the fractional derivative notation. I'm going to blend both of them in here. Capital F prime of x, using our u substitution, equals df du, which we can find using the first part, times du dx. What is capital F, or what is df du, f prime of u? Well, apply the first part, it's just sine of u. What's du dx? Well, we have x to the half here, x to the half, x to the negative half. For these computations, you could leave it as half x to the negative half. I'm going to write that as the 1 over 2 root x, because I think that looks nicer for this one. Times 1 over 2 x. And what do we get here? Well, we still have a u. We can get rid of that u. So it equals, I'm going to leave it as a I don't like how that looks. I'm going to pull that 1 over 2 root x out front. I could write this as one fraction. But I think this looks a little better when you keep the 1 over 2 root x out front. So here for part B, we made a u substitution which reduced our initial equation to an equation on which the first part applied. And then we used the chain rule, this first derivative from the first part of fundamental calculus, 1 over 2 root x from our rule, and then replace u with root x since u equals root x. Any questions about part B? Now, before going on to part C and D, which I haven't written yet, I'd like to make a couple observations about parts A and B, especially about part B, because this is a lot of writing. Is there a way that that lot of writing could be reduced? Well, there can be if we're careful in our observations. Right here, I'm just going to write the answer of part A, so I can reference it at home. And for part B, I'm going to erase everything but the answer. So what actually happens in part A is reasonably complicated because it goes through the fundamental theorem of calculus. But the computation can be greatly simplified. Now, we did it in one line, but what actually happened? Or how can we view that computation? Well, when that's just an x, the first part says that we can find capital F prime by replacing all t's with x, reimagining the integrand as a function of x. And that was part A. What about part B? Well, part B says still if there's a number as your lower bound. It says if we have more than just an x up here, so here we have a root x, that's more than just an x, we can still make a similar substitution. Now, if you just replaced all t's with this function of x, well, that part still appears in our answer, but it says we have to use chain rule when that's more than just an x. So we can replace all t's with that and apply chain rule. And chain rule says derivative of root x is 1 over 2 root x, or half x to the negative half, and be multiplied by that. So we really have another derivative rule that we could add to our list, making it, 17, I believe. Any questions about these first two? So for parts C and D, which I'll write in a moment, I will use this shortcut observation rather than the substitution. So any questions about, rather than the use substitution, any questions about A or B? Okay, so let's do two more, parts C and D. At the beginning of this, I said we're going to use some definite integral properties. We haven't used any yet. We will use them, some of them, in parts C and D. Let's make it a 4. 4 is a number. X cubed to 4 of what? Now when we had sine, let's do a cosine here. And part D. Oh, I should be writing capital F equals capital F of X. Part D, capital F equals what? Let's just leave it with x's since this is our first example. Let's do x cubed to x to the 7th of let's do 1 over x to the 4th, or t to the 4th plus 1. So in these computations, the actual integrand is minorly relevant, but not majorly relevant. So let's do part C first and then part D next. So part C, we have the integral from x cubed to 4. Now, the first observation is that we want the derivative. The first part of the fundamental theorem doesn't apply to this integral because the first part says we need a number to be the lower bound and our x's to be the upper bound. So here we have, I don't really have to rewrite this. Yeah, I know I already started. Here, we have a number as our upper bound and a function of x as our lower bound. But what we can do to make the first part apply is use a definite integral property. Definite integral property 2 from that list says that we can flip bounds around, but there's a cost. A negative is the cost. So if we flip the bounds around, well, now over here on the rightmost side, the bounds are in a form on which the first part of fundamental theorem of calculus applies. And to get them in that form, we needed to throw a negative on. Any questions about applying that first property? So now over here, we can apply the first part of fundamental theorem of calculus. So capital F. Well, we also would have to apply the chain rule since we have x cubed on top and not just x. Well, we have a negative. We have cosine, replace all t's with an x cubed, and then multiply by the derivative of x cubed using chain rule. So 3x squared is from chain rule. The negative is from flipping the bounds, cosine of x cubed from the first part of fundamental theorem of calculus. Any questions about that? Okay, so let's do. Just writing myself a note over here to be sure I mention this. So let's do part B, or part D. Part D, we now aren't in case, or part A, we aren't in part A, we aren't in part B, we aren't in part C, because for part D, notice we have x's as our top bound and x's as our lower bound. So let me write this up here. We have x's as our top bound, we have an x to the 7th up there, and we have x's as our lower bound. First part of fundamental theorem of calculus applies when the lower bound is a number. But what can we do? Well, we can use property I'm going to go across the center line so it's not in the way. We can use property 5 of definite integrals to break this into 2 integrals. What would that look like? Well, you could write it in the opposite way, but I'm going to write it like this. We're going from x cubed to x to the 7th. Well, let's put a number between them. X cubed to, how about 1? 1's a good number. We're going to split this integral at 1. So instead of going from x cubed to x to the 7th, we're going to go from x cubed to 1 and 1 to x to the 7th. Now, well, any questions about splitting that up? Well, you may wonder, how did I choose 1? Well, there are 2 things that have to go into consideration when doing that. 1, it has to be a number. That part is the easy part. The other part, the number can't be at a point where this integrand is undefined. So if this said t to the 4th minus 1, I couldn't choose 1 because that would put a 0 in the denominator. I'd have to choose something like 2. But t to the 4th plus 1 is always non-zero, at least for real numbers. So it has to be a number and the bottom of a fraction. Well, and the integrand has to be defined at that. Here, 1 works, so I use 1. But we now have two integrals on our right-hand side. This second one, we can apply arguments we've done, or we used in part B, because we have a 1 at the bottom, we have a number at the bottom, and a function of x in the top, x to the 7. But this first integral puts us back in case C, where the lower bound is not a number, the upper bound is not a function of x. So what we would have to do there is flip it around so that the first part applies. So we'll throw a negative on the first, flip the bounds, and we can leave the second alone because we can apply the first part to that. And now we can find our derivatives as in parts, well, part B really, but this one was a little more like part C. So capital F prime of x. Again, for these, you could write out the substitution with chain rule. I think for these especially, that's a little more writing than, when you do a couple of these, you realize that the chain rule argument is identical to the previous chain rule arguments. So it's definitely good to practice doing these in one step. So for this first piece, replace all x's, or replace all t's with x cubed. What do we get? Well, we have x cubed 4 times, that gives you 12 x's. Multiply by derivative of x cubed, which is 3x squared. And don't forget the negative. Plus, same thing here, but with x to the 7. If you have x to the 7 4 times, that gives you 28 x's. One in the numerator, multiply by the derivative of x to the 7. Any questions about part D? Okay. So we have another derivative rule, and we can use chain rule with that. Let's do next some second part of the fundamental theorem of calculus computation, some definite integral computations. So example. There will be probably 7 or so examples here. I'm not going to write them all right at the beginning because I don't remember for that. Evaluate each definite integral using the second part of the fundamental theorem of calculus. FTC part 2. I'll start by writing 2. Integral x cubed minus 2x with respect to x from 1 to 3. Part B, integral from 1 to 8 of the cube root of x with respect to x. And then this list will probably have maybe 7. Let's see how these first 2 go. From there. So here we're evaluating definite integrals. What does the second part of the fundamental theorem of calculus say? The second part of the fundamental theorem of calculus says that the integral can be found by evaluating says antiderivative, that went a little off screen. The second part says a definite integral can be found by evaluating any antiderivative at the endpoints, subtracting what you get at the top endpoint, or taking what you get at the top and subtracting what you get at the lower bound, lower endpoint. So what can we do here? Well, maybe I'll just write it like this. Yeah, I'll write it like this. Equals, and we'll go over to this side. Well, to evaluate this, we need an antiderivative of x cubed minus 2x. How can we find an antiderivative of x cubed minus 2x? Well, we can use our antiderivative rules. Quarter x to the fourth minus x squared. So we have a couple power rules. 3 plus 1 is 4, divide by 4, x to the fourth. 1 plus 1 is 2, divide by 2, which makes the coefficient -1, make it x squared. A couple power rules. But any antiderivative, right here, if we, this gives all antiderivatives. Here we need any antiderivative. You can choose any constant you want. I would recommend 0, because there's less writing to do if you choose 0. It'll work for any constant. But this isn't all that we want. We want to evaluate this antiderivative at 3 and at 1 and subtract that. And we have some notation for that. A large vertical bar with a 1 at the bottom and a 3 on top. We can use to notate that we want to evaluate this at 3 and 1 and subtract what we get at 1 from what we get at 3. What do we get? Well, we need this antiderivative evaluated at 3. 3 to the fourth is 81. 3 squared is 9. So that's what we get when we evaluate at 3. Subtract what we get when we evaluate at 1. Let x equal 1. We get 1/4 minus 1. And we want to subtract all of that. It says minus f of a, not minus just the first term, minus all of this antiderivative evaluated at 1. And now we just combine these numbers. With these, I usually like to combine the fourths and the whole number separately. 80 1/4 minus 1/4 gives 80 fourths, also known as 20. -9 minus -1, -9 plus 1 gives you -8. 20 minus 8 is 12. So for part A, well, any questions about what we did for part A? So to do this computation, we needed an antiderivative. We chose the one where the constant is 0. Evaluate at the endpoints and subtract. So when we did indefinite integral computations, the computation looked a lot like this first part, except, well, there weren't bounds, and we stopped here and added a constant c. So the computation we're going to go through for definite integrals using the second part of fundamental theorem of calculus does look a lot like the computations we did for indefinite integrals. This results in more numbers, but there are a few different ways you can see indefinite integrals and definite integrals relating. One of them is in this part A computation, because if we wanted the indefinite integral, the indefinite integral would just be the indefinite integral, all antiderivatives. But the definite integral, take one antiderivative, let the constant be 0, evaluate at the bounds, and subtract. Any questions about part A? Okay, let's now do part B. Part B said what? Integral cube root of x from 1 to 8. Well, we need an antiderivative of the cube root of x. How do we find that? Well, we can use the power rule. How can we use the power rule? That doesn't look like power. Well, the cube root of x is an abbreviated way of writing x to the 1/3. And now we can apply a power rule. What's 1/3 plus 1? Well, 1/3 plus 1 is 4/3. What happens when you divide by 4/3? Well, that's the same as multiplying by 3/4. So there's an antiderivative, let the constant be 0. Choose the antiderivative with the constant being 0, so you have less writing and fewer numbers to consider. Evaluated from 1 to 8. What happens when we evaluate it at 8? Well, what's 8 to the 4/3? Cube root of 8 is 2. 2 to the 4th is 16. So we have 3/4 times 16. Minus what happens when we evaluate at 1. 1 to the 4/3 is 1. So we have 3/4 of 16 minus 3/4 of 1. What's 3/4 of 16? 12. What's 3/4 of 1? 3/4. 12 is 48/4. So we get 45/4 here. Any questions about part B? Okay, let's do some more. Let's do a couple with trig. Part C. Part D. Let's do these two things. First, we have integral cosine x from what, pi to 2 pi. Well, we need a function whose derivative is cosine of x. Do we have it? Yes. The derivative of sine of x is cosine of x. We're evaluating this from pi to 2 pi. In all of these, I guess I didn't mention this for parts A and B. Once you get here, you can check your work by taking the derivative of this piece. Derivative of sine x is cosine x. And in the first one, you had a quarter x to the 4th minus x squared. The derivative would be x cubed minus 2. In the second one, you had 3/4 x to the 4th. Power rule, 3/4 and x to the 4th. Why did I say that? 3/4 x to the 4/3. Power rule, 4/3 and 3/4 all cancel to 1. 4/3 minus 1 is 1/3. Here, derivative of sine is cosine, so this works. And what do we want to do? Evaluate at the endpoints and subtract. Sine of 2 pi minus sine of pi. What are they? Well, they're both 0. Why are they both 0? Sine of 2 pi, the y value there, 0. Sine of pi, y value there, 0. So 0 minus 0 here gives us 0. More on that after we do these computations. Any questions about part C? Okay, part D. Integral 0 to pi over 4 negative secant x tangent x with respect to x. We need a function whose derivative is negative secant x tangent x. Well, yeah, I'll write this step out. There are a few different first steps you can do here. You can jump straight to the antiderivative. But what I'm going to do, I'm going to pull that negative out, because we can do that. You know, it's just a number. You can pull that out by property 4 of definite intervals. We need now a function whose derivative is secant x tangent x. Well, the derivative of secant of x is secant x tangent x. And the negative carries through, evaluate from 0 to pi over 4. And what do we get? Well, we get negative secant pi over 4 minus what we get when we evaluate at 0, minus negative secant of 0. So minus negative secant of 0. And what do we get here? So minus negative gives us that plus. Negative root 2 plus 1. Why do we get negative root 2 plus 1? Well, secant of 0, we can find cosine of 0 is 1, flip it around, 1, flip it around is 1. Secant pi over 4. Well, take the pi over 4, pi over 4, pi over 2 triangle. Take the angle pi over 4. Cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. Secant pi over 4, root 2, and there's that negative in front. So you get negative root 2 plus 1. Any questions about parts C or D? Let's actually do 4 more. 1, 2, 3, yeah, those 4 will be good. So E and F. Now, this integral notation and the computation, you know, there's a lot of things I'm writing in different sizes to help keep me organized. You know, blank paper, I find, especially for integrals, it gets very much in the way. Part E, integral 1 over x to the 4th from 1 to 2. Notice, well, let's write part F. Integral from 1 to 2 make it a minus. Let's do these two. So first, we have an integral from 1 to 2, 1 over x to the 4th. Well, we can't just jump straight into that quotient. Integrals don't work that way. But what we can do is see if we can rewrite the quotient so that our antiderivative rules apply. And here we can do that by rewriting x to the 4th as x, or rewriting x to the 4th in the denominator as x to the negative 4th. Now, the power rule for antiderivatives applies. Negative 4 plus 1 is negative 3. Divide by negative 3. divide by negative 3. So we have negative 1/3 x to the negative third. And we're evaluating from 1 to 2. So what do we get here? Well, before even evaluating, I'm just going to write this a little nicer. And on negative exponents, I always, I'm okay if you leave negative exponents, but for simplifying numbers, I never like thinking about negative exponents if I don't have to. It's easier to organize it as a fraction now than it is later. So what do we get here? Well, evaluate at 2. 2 cubed is 1. 2 cubed is 1. 2 cubed is 8. I must have been looking at one of these ones when I said 2 cubed is 1. 2 cubed is 8. 8 times 3, 24. And that negative carries along. Minus what we get when we evaluate at 1. When we evaluate at 1, we get negative 1/3. So minus negative 1/3. 1/3 is 8/24. 8 minus 1 is 7. We get 7/24 here. Any questions about this one? Now, I'd like you to notice there are a lot of negatives in this one, and in part, what was that, part D? Yeah, and in part D there were negatives. If you wanted to get rid of these negatives, so I'll just say if you wanted to get rid of the negatives, what you could have done was said that that equals 1/3 x cubed, but flip the bounds around. Flipping bounds around, the difference is a negative. And then you get 1/3 minus 1/24, that line flipped around, which equals 7/24. So you could have done this in part D as well. But you don't have to. You could, whichever way you prefer. Sometimes it's nice to have fewer negatives to deal with, especially in this step when you have to subtract the negative. Whatever. Any questions about part E? Okay, how about part F? X to the 4th minus 2 over x squared from 1 to 2. Now, we can't just jump straight into the quotient. But can we rewrite this in a way that will make our antiderivative rules apply? We can. You better be able to if I'm asking the question. What can we do here? Well, we can split this fraction. Split the fraction over x squared, meaning we get x to the 4th over x squared, which is x squared, minus 2 over x squared. So we get, okay, let's actually do after this one. Yeah, okay, 2 more, that'll work. So we split this fraction over x squared, divide each piece by x squared. You could say x to the 4th over x squared is x squared. Negative 2 over x squared, negative 2x to the negative 2. And now we can apply some power rules here. Any questions about splitting the fraction? Power rule on the first, 3rd x cubed, power rule on the second. 2x to the negative 1, where did that come from? Negative 2 plus 1 is negative 1. Divide by negative 1, negative 2 divided by negative 1 gives us that positive 2. We're evaluating from 1 to 2. I'm going to continue the computation at the top. Actually, I have some more here. What does this equal? Well, again, I'm doing evaluating. I don't want that negative exponent there because then in the computation, when we think about all those numbers, we have to think about the sides of fractions. So instead, I'm just going to write this 2 over x now. Evaluate from 1 to 2, and what do we get? Evaluate at 2. 2 cubed is 8. So 8 thirds. 8 thirds plus 2 over 2. 8 thirds plus 1. And then we subtract what we get when we evaluate at 1. Evaluate at 1, you get 1/3 plus 2. What do we get here? 8 thirds minus 1/3 is 7 thirds. 1 minus 2 is negative 1. 7 thirds minus 1 is 4 thirds. Any questions about that one? Or part B? So in this one, we had to split the fraction so that our power rule and so on applied. Here it's just power rule. Let's do 2 more. E, not E. G. Integral, and then we'll do an example, and then we'll make an observation. 0 to 2 of e to the x. Now let's, yeah, okay, e to the x. The worksheet has something like e to the x plus 2. Or maybe that's a homework. And part H, maybe should have made that part H. Actually, let's do 3 more. And then these will both illustrate something just part H1. Okay, so let's do GH and then we'll do M9. Part G, e to the x from 0 to 2. Well, we need a function whose derivative is e to the x. Derivative of e to the x is e to the x. We're evaluating from 0 to 2. Evaluate at 2, you get e squared. Evaluate at 1, evaluate at 0, you get e to the 0. E to the 0 is 1. Questions about that one? Okay, how about this next one? Well, again, we have a quotient. So we can't just jump straight into the quotient. But what we can do, just like in well, in 2 other ones we did, we can split the quotient. Root x divided by x, x to the negative half. 1 divided by x, well, it is x to the negative 1, but recall from our derivative rules, our indefinite integral rules, our antiderivative rules, the power rule didn't apply when the exponent was negative 1. But we did have a convenient logarithm rule which did apply. And for that, I usually like to just write it as only 1 over x. But over here for this first piece, we are going to need a power rule, so I wrote it as its power form, in its power form rather than 1 over root x. Power rule, 1/2, there's a -1/2 plus 1 is 1/2. Divide by 1/2 plus 1 over x, the derivative of log of root x, or log of absolute value of x is 1 over x. Here, technically, well, if I made those bounds something like, negative, well, I guess I wouldn't have negatives with the square root. But if the bounds had negatives in them and you had a logarithm, you would have to consider that to be an absolute value. But here, we're going to see that the absolute value is redundant. But what do we get when we evaluate? We get 2 root 2 plus log of 2. Let's write this somewhere else. I don't want to go off the screen here. Evaluate at 2, you get 2 root 2 plus log of absolute value of 2. Absolute value of 2 is 2. Minus what happens when you evaluate at 1. 1 to the half is 1, so minus 2 plus log of 1. E to the 0 is 1, so log of 1 is 0. And what do we get? 2 root 2 plus log 2 minus 2. An example yesterday where we had a lot of 2's. This one might have even more. Especially if you interpret that as 2 to the 1/2. Any questions about part H? Now let's do one more. Let's do part I. 3 plus x root x 0. We'll leave part H on the board while we do part I. Three plus x root x with respect to x. Now, well, you may notice in a lot of these I write parentheses, pretty much all of them I write parentheses between the integrand and dx and the integral sign. That's technically, and sometimes you see it not written. The reason I write it is because it makes me keep in the back of my mind the fact that we actually are, this notation and its setup are a result of our rectangle approximation. And even in these integrals, you can see the remnants of the rectangle approximation. Function times some sort of change in x. Now, there is a reason for all of this notation. But what do we get here? Well, first I'm going to write this in its power form. X times x to the half is x to the 3/2. We're evaluating from 0 to 1. What do we get? Well, 3 is a constant. The derivative of 3x is 3. How about x to the 3/2? 3/2 plus 1 is 5/2. Divide by 5/2 gives you 2/5. There's a positive sign. Evaluate from 0 to 1. Take the derivative of this, you do get 3 plus 5/2 and 2/5 cancel. 5/2 minus 1 is 3/2. Now evaluate from 0 to 1. Well, evaluate at 1, what do you get? 3 plus 2/5. What about when you evaluate at 0? Well, you get 0 plus 0. 3 plus 2/5. 15 plus 2 is 17. So it's 17/5. Any questions about this one part I? So I'd like you to notice something about parts G, H, and I. Notice in part I, the fact that one of those bounds was 0 made our eventual computation, much less tedious, because we got zeros. In part G first, in part G, we had the integral e to the 2x from 0 to 2. Notice that when you substituted 0 in part G, you did get a number. So in part I, evaluating at 0 resulted in 0. In part G, evaluating at 0 did not result in 0. It resulted in 1. So sometimes, sometimes when you're grading calculus, a class of 50 students, there are usually anywhere from about 5 to 10 who just ignore what happens at 0. But notice from part G, what happens at 0 may not always be 0. In part I, it was 0. Any questions about that? Now, one other thing I'd like you to know is all of those where we had fractions, part H, part what was it, G and or parts E, F, and H, I believe, had fractions. In all of those, we couldn't have a bound of 0. They all, I believe, I wrote 1 to 2 in all. But why didn't I put a 0 in any of them? Well, because that integral that is right now written after letter H is not doable in Calc 1. Why is that? Well, notice the integrand root x plus 1 over x is not continuous on 0 to 2. It's not even defined on all of 0 to 2 because it's not defined at 0. To do that computation, you would have to, well, you'd have to take Calc 2 first of all, but you would have to, in order to apply the fundamental theorem of calculus, you would have to review this as a limit. More details on that halfway through Calc 2, and maybe a third of the way through Calc 2. And maybe a little more than a third. But the what was I about to say? The integrand always does have to be continuous on the entire integral in order to evaluate the integral. In Calc 2, you go over that one. In Calc 1, that won't really become relevant. If I ask you to do an integral, it will be doable, unless I have a typo, in which case, remove the question from the example. But there won't be a typo. Let's do one more example. Find the area. X squared plus 3, which area? 1 to 3 is what we did in week 2. So find this area. Well, there are 2 ways, technically, we could do this. One, we could set up the limit, evaluate the limit. Alternatively, we can use an integral. That area equals the integral from 1 to 3 of our function. And what does this equal? Well, powerful third x cubed. Derivative of 3x is 3. Third x cubed plus 3x. Evaluate from 1 to 3. what do we get? 3 cubed is 9, or 3 cubed is 27, divided by 3 is 9. 3 times 3 is 27. Subtract what we get when we evaluate at 1. And what do we get? Maybe this isn't the example we did. What do we get? We get 36 minus 3 is 33. 33 minus 1/3 is 32 and 2/3. And what is that? I thought this was the example we did in area under a curve. Oh. Did I do something wrong? X squared plus 3. I thought this answer was supposed to be 44/3. Oh, jeez. Well, you should have stopped me. Three times 3 is 9. There we go, that looks better. 9 plus 9 is 18. 18 minus 3 is 15. 15, we didn't do the 1/3 yet. 15 minus 1/3 is 44/3. So in week 2, when we did area approximation, I said that the exact area of the running example for a good portion of that video was 44/3. Right here, we did verify it. In week 2, I said we would show this using the limit. I was planning on doing that today, but I guess I won't. I would rather, with a week and a day left in the class before the final, I would rather that your practice be on computations using the 2 parts of fundamental theorem calculus. So because of that, where's my worksheet? Because of that, worksheet 5, problem 9b, evaluate using limit definition. We didn't cover that, and we won't cover that, so you don't have to worry about that. But in the solutions, which will be posted by tomorrow morning, in the solutions, I did go over 9b in detail. So if you would like to see that limit computation, definitely, well, even if you wouldn't like to see the limit computation, it's very worth looking at the solutions to 9a and 9b once I post them, just to see how nice the fundamental theorem of calculus is. Part A, right here, I don't know if this is showing up on camera clearly. For what is shown, there are 1, 2, 5 lines. Part A takes up the first line. Part B, oh no, there are 6 lines, there's one by my thumb. Part B takes up the next 5 lines. And parts A and B combined illustrate how nice the second part of the fundamental theorem of calculus is. The second part of the fundamental theorem of calculus says we don't have to do a computation like is in 9b if we want the definite interval. It says we can use a computation like in part A if we can find an antiderivative. So while I won't on the final ask you to evaluate the limit like in 9b, it's definitely worth some time in the next 8 days just comparing once I post the answers for 9a and 9b from worksheet 5. Definitely look at that just to see how nice the first part of fundamental theorem of calculus, or the second part of fundamental theorem of calculus is. So any questions about anything we've covered today? Okay, so next week there is one more topic. It will be a video. It'll be about a half hour. I will also post one page of notes with a result that you don't necessarily need to know, but it's another. Well, I'd like you to practice these computations before seeing it, so I'm not going to do it this week. But I will post one page of optional notes that would make some computations a little easier, although it's not necessary. So any questions? Okay, so there is that one topic next week. Next Wednesday, probably on, so there's a worksheet for next week also with one problem. I will post that and its solution. I'll post the worksheet, I don't know, maybe Saturday, the video, also Saturday. Since you have homework tomorrow. I'll post the solutions for worksheet 6, next week's worksheet, on Monday. And sometime over the weekend, I will send you a final exam review document. On Wednesday, from 1 to 3 in here, we will go over solutions to the final exam review document. That shouldn't take the entire 2 hours. There were a couple issues with 1 or 2 of the problems on this exam. I guess I'll go over that during the final exam review. I'll give you a chance to look at the solutions to exam 2. But next Wednesday, we will have a final exam review document posted this weekend. And on Thursday, those 2 hours will be just an office hour, which I'll send you a link to right before 1 o'clock. So any questions?